Hello everyone, my name is Minghao Liu from Institute of Software, Chinese Academy of Sciences. Here I will give a brief introduction of my work, learning the satisfiability of pseudo-Boolean problem with graph neural networks. As we know, many effective heuristics in solving constraint satisfaction problems rely on the observation and idea from human experts. The deep learning systems have improved the state-of-the-art standards of many AI tasks across domains. This also inspired us to apply learning-based approaches to solve constraint satisfaction problems, which may capture the specific structures of the problem from benchmarks, so that some effective implicit heuristics may be learned automatically. An important question is the choice of model. Compared with convolutional neural network and recurrent neural network, we believe graph neural network is a promising choice. More specifically, we choose to learn the satisfiability of pseudo-Boolean problem. We believe it provides an important setting for investigating the capability of graph neural network in extracting features of CSPs with numerical constraints. Our GNN model contains 4 parts: normalization, graph construction, message passing, and readout. We prepare 2 different pseudo-Boolean problems for the experiments: 0-1 knapsack and weighted independent set. These 2 problems have very different distributions. The model can converge and achieve more than 85% classification accuracy when the number of variables is no larger than 40. From the results, our model is believed to have learned some features related to the satisfiability of problem. Moreover, the accuracy of our model outperforms that of NeuralSat, a GNN model for solving the satisfiability of set formulas in multiple dimensions. So our model can be seen as a generalization of it. We hope the model can provide a basis for a series of future work on learning to solve different CSPs with numerical constraints. If you have any questions, please feel free to contact. Thanks for your attention. Hello everyone, thanks for coming to my talk. I'm Minghao Liu from Institute of Software, Chinese Academy of Sciences, and it's my great pleasure to introduce my work here. The paper is Learning the Satisfiability of Pseudo-Boolean Problem with Graph Neural Networks. This is a joint work with our group. Here is the outline of the talk. It contains 4 parts. First, I will introduce the motivation of the research, and then I will briefly introduce pseudo-Boolean problem and present the architecture of our GNN model. Next, the experimental settings and results are reported. And finally, there is the conclusion and some discussion about future work. As we know, machine learning, especially deep learning, has shown great power over the past few decades. Deep learning systems have improved the state-of-the-art standards of many AI tasks across domains, such as computer vision, natural language processing, and game playing. The success of deep learning has also inspired us to apply learning-based approaches to solve constraint satisfaction problems. For example, many effective heuristics in solving CSPs rely on the observation of human experts. So there is an interesting prospect that the end-to-end neural networks may have the ability to capture the specific structures of the problem from benchmarks, so that some effective implicit heuristics may be learned automatically. An important question is the choice of model. We know that several deep learning networks have been developed, such as convolutional neural network and recurrent neural network. However, the structural information of CSPs may be partially lost when represented as matrix or sequential input. So it is necessary to find more powerful models to represent and solve CSPs. A promising choice is graph neural network. We won't go into the model in detail, but you can find lots of tutorials online, such as the bottom link to a video from Microsoft Research. Here, we only briefly introduce the input and output of Jian. The input is a graph representation of a problem. For each node, there is an embedding vector of real numbers, which is also called distributed vector, to represent the information of this node, like many other deep learning models did. The output is the same graph with new embedding vectors, which is computed by Jian and contains the context of each node in graph, such as the information of its neighbors and the graph structure. We believe Jian is a good choice for solving CSPs in 3 points. First, in the past few years, it has shown its power of learning on graph, which is a kind of non-Euclidean structured data. Second, we know that many CSPs can be naturally represented as graph, and many of them are strictly defined on graph, such as TSP, vertex cover, and independent set. Third, there have been some successful early attempts, such as NeuralSet, a GNN-based model for solving the satisfiability of set formulas. NeuralSet is based on message processing neural network, which is a commonly used framework of GNN. It represents the set formulas as bipartite graph. The nodes correspond to literals and clauses. If a literal appears in a clause, we build an edge between the corresponding nodes, so it's quite intuitive. Here is an example of the graph representation of a simple set formula contains 2 variables and 2 clauses. The experiments show that it has 85% accuracy on the dataset of 40 variables per instance. Next, I will talk about the problem and approach. The success of NeuralSet encourages us to further explore the performance of GNN on CSPs with numerical constraints. So we choose to study Pseudo-Boolean problem. Pseudo-Boolean problem, which is also called 0-1 integer programming, has received much attention in a lot of real-world applications. The definition of pseudo-Boolean problem is here. Given a set of linear constants, decide if a set of assignments to the Boolean variables exists, so that all the constants are satisfied. More specifically, we choose to study this problem for several reasons. First, it has been proven to be an NP-complete problem. Second, many CSPs can be easily formulated as PB constants, so the model could handle various CSPs without modifying the structure. Third, because the PB constants involve integer coefficients and constant atoms, we believe it provides an important setting for investigating the capability of GNN in extracting features of numerical constants. The pipeline of our model is as follows. There are mainly 4 parts: normalization, graph construction, message passing, and readout. Learning from some common practices, we adopt some rules to transform different kinds of constants into normalized form. Firstly, we replace some variable x with its negation if its coefficient is less than 0. After that, if the constant atom is non-positive, the constant is a tautology and could be removed from the problem. If it's positive, it could be set to 1 by dividing both sides of the inequality by the value of constant atom. After the normalization, we can generate the graph representation of PB problem. We set 2n nodes for the variables and their negations, and m nodes for the constants. Same as neural set, the age represents a variable or its negation is contained in a constant. But the difference is that we build a weighted bipartite graph, where the age weights are represented by the coefficient values. Now let's go inside the Jian model. It is also an implementation of message passing neural network. As mentioned above, for each node, there is an embedding vector to represent its information. In each time step, the information is firstly passed from the variables to constants, and then in the opposite direction. So the node embeddings are updated iteratively. After the message passing process, the features related to the problem structures are contained in the node embeddings. And the last part. Firstly, the readout function vvote is to decode the embeddings of each variable node into a real number. And then we obtain the final prediction by computing the average number of all the outputs of vvote for the variable nodes. The model uses the real satisfiability of the problem as a label for supervised learning and minimize the binary cross-entropy loss of the label and the prediction y-hat. We prepare two different problems for the experiments, 0-1 knapsack and weighted independent set. We generate the datasets in the following steps. First, we generate the original instances, which are optimization problems, and then the instances are transformed to the decision problems by adding a random offset on the optimal solution. This value could be called a bound. The third step is to build the weighted bipartite graph. 0-1 knapsack problem is famous in combinatorial optimization with a very simple structure. It can be formulated as these two PB constraints. We generate the weights and profits of atoms under the distributions proposed by Pzinger. We can also model the weighted independent set problem as PB formulas. The random graphs are sampled from the ER model with parameter p equals to 0.5, which corresponds to the case where all possible graphs on n nodes are chosen with equal probability. We train and test our model with different settings. Firstly, here is the result of classification accuracy. For 0-1 knapsack, we set up 3 groups of experiments with different number of variables, and for weighted independent set, we set up 4 groups. When the number of variables is no larger than 40, the model can converge and achieve more than 85% accuracy both on the validation set and the testing set. When it is expanded to 100 variables in 0-1 knapsack problem, the accuracy is still up to 79%. From the results, Our model has learned some features related to the satisfiability of problems. Besides, it can be found that the generated instances have very different distributions, whether in terms of the average number or length of the PB constants, which indicates our model can work on different distributions without changing the structure. Moreover, we make a comparison about our model and neural set. We transform the PB constants into set formulas and train these two models on the same benchmark respectively. We can see that the accuracy of our model outperforms that of neural set. The reason may be more variables and clauses are introduced during the transformation, which makes the model harder to converge. In the last two lines, the SR data consists of random set formulas defined in neural set paper. Here the performance of our model is also comparable with neural set, so that our model can be seen as a generalization of it. Another point of concern is the time spent for solving. It can be found that, compared with the classic solver Cplex, our model takes only less than 10% of time to return the prediction for each instance. In addition to the lower computational amount, another reason is that the instances can be input in batches, and the solving process is accelerated with parallelization. The results also inspire us a promising scenario of the model when a large number of similar instances need to be solved with high frequency. We are also interested in whether the model trained on small-scale data can work on larger-scale data. We train our model on the datasets of 10 to 40 variables, and test on datasets in the range of 10 to 80. The figure shows the change in accuracy when testing our model, which indicates that the generalization performance is affected by both the structure and the difficulty of the problem. Finally, let's make a conclusion. We propose an end-to-end GNN model to solve pseudo-Boolean problem, which is a general representation of constant satisfaction problems with numerical constants. The model has been experimentally confirmed to achieve high accuracy on different benchmarks, and the model can be seen as a generalization of neural set. We hope the model can provide a basis for a series of future work on learning to solve different CSPs with numerical constants. First, we have to acknowledge that the scale of learnable problems is small, and it should be improved to handle larger scale problems. Second, we will try to decode the variable assignments from the trained model so that it can be called a real solver. Third, we hope the model could be integrated in a branch and bound or restart scheme to perform approximate pruning and actually helps to improve the state-of-the-art CSP solvers on those hard benchmarks. We believe that the development of graph representation learning will help the model to extract more accurate features, thereby reducing the heavy manual work of designing heuristics in the future. That's all. Thanks for your attention.